Hi Wildcats. It's a tutorial on Unit 0 focus question number 3, graphical and mathematical models. So today we're going to talk about why we use them, what they are, and how we can analyze them. So let's start by telling you something that you probably already know. Math and science are better than English. And you can tell them I said that. In some cases. So here's a physics relationship in words. In physics, mass and energy equivalents explain the relationship between mass and energy. In a physical system, the kinetic energy of the system is the equivalent to the mass of the system multiplied by the square of the speed of light in a vacuum. Because of this relationship, it is also possible to determine the mass of an object which gives off a certain amount of energy. This is possible by determining the quotient of the kinetic energy released and the speed of light in a vacuum. Since the speed of light in a vacuum is a constant, the relationship between mass and kinetic energy is always the same. Okay, so that is a lot of words and confusing, and you have to stop and think about it and blah, 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 when in reality, math and science allows me to say that exact same thing with that. So English has its place. I'm just giving the English teachers a hard time. In reality, though, for some things, we can much more simply and clearly communicate it using math. So this would be a perfect example of that. This whole paragraph right here can be summarized mathematically using the relationship energy is equal to mass times the speed of light squared. So let's talk about what this mathematical models like this actually are and how we come up with them. So a mathematical model is something that communicates the relationship between variables. So this is a mathematical model, is the mathematical model for the potential energy of an object. And because I know what these letters represent, I can say the potential energy of an object is equal to its mass times acceleration due to gravity on Earth times the height of the object. So just by these letters, I know all of that. And because of that, if I can use it predictively. So for example, if I know the mass of an object, I know the acceleration of gravity on Earth, and I know how high off the Earth I'm holding it, I can calculate precisely how much energy it has, potential energy it has. And maybe even more importantly, I can do this for anything just by simply rearranging what it is. So for example, let's say I want to know, all right, I want this bowling ball to have some amount of potential energy so it can make it down a hill or a roller coaster. I need a roller coaster car to have enough potential energy to make it up the next hill. Well, I could figure out how much energy it would need if I know the mass of the cars and I know the acceleration due to gravity here on Earth. I could solve exactly how high I need that car to be when it starts. And so I can figure out other things about scenarios related to potential energy just by using simple algebra of rearranging this equation. And again, to do that with words is just not going to work. So math models are really just a fancy way to say equations. And because we can rearrange equations and use them with numbers, we can make predictions about any of the variables in that equation. Let's talk about rearranging them. You will need to. So one thing, I like to use this equation for this example. I looked it up years ago. Don't even remember what it's for. I'm guessing this is mass, but I don't remember. And frankly, it doesn't matter. If you tell me you want to know something about C sub p, okay, well, I can use algebra, divide both sides by m over delta t. Divide both sides by m over delta t. M cancels, and so now I can say that whatever the heck C sub p is, whatever it stands for, it is equal to Q over M, I'm guessing that's mass, times change in T. But again, I can tell you about the relationship between these things. I could tell you that this variable, C sub p, is directly related to Q, and it's inversely related to M and change in T. And I don't need to know anything about them. Just by looking at this equation and how it's written mathematically, I know that. So that's the reason I like to use this one. This one over here is probably the hardest math you'll have to do in this entire class. So I often hear students say, well, I don't want to take physics, or physics is too hard because of the math. Like, the hardest math you'll have to do is be able to solve for G in this equation all year. So let's see if we can do that together. Or let's see if you can do it. So pause the video, see if you can solve for G. If you can, then in the first few weeks of school, you are able to do the hardest math this entire class will ask for. So give that a try. All right, back at it. So how do we want to do this? Well, I want to start by grouping this. And then there's a couple things we can do. Should we get rid of the 2 pi? Let's get rid of the 2 pi. Okay, so divide both sides by 2 pi. 2 pi, that's gone, that's gone. So now I have t over 2 pi is equal to the square root of L over G. I'm looking for G, so I got to get it out of the square root. Square both sides. So now I'm left with, this cancels the square, so I'm left with t squared is equal to, this 2 distributes to everything, so 4 pi squared is equal to L over G. And there's so many ways that you can do this. I'm going to do it like the long way. I'm going to multiply both sides by G. I know, this is the annoying way to do it. So now I'm left with t squared times G is equal to 4 pi squared, or over 4 pi squared is equal to L. Now to get rid of this, I have to multiply both sides by 4 pi squared over t squared. That's going to get rid of that, and that, and that, and that. I got to do it over here. So 4 pi squared over t squared. And boy, oh boy, G is equal to L times 4 pi squared all over t squared. Okay. So, I mean, I'm not going to say that's easy. You got to know the rules of algebra and moving stuff like that, but this is something that you've all done in any algebra class that you've taken to some degree, and it's basically the hardest math that we'll do in here. So, again, we're just using algebra rules to rearrange and find the relationship between these things. Okay, so those are mathematical models. Let's talk about graphical models. Graphical models allow us to visually represent the relationship between variables. So in other words, let's just look at this graph. This graph shows me the relationship between sales and temperature. Temperature is down here, so this is our independent variable. So it looks to me like as temperature increases, sales also increase. Okay, so just by looking at this picture, no math, no nothing, I know the relationship between them. According to this graph, as temperature increases, so does sales. I just described the relationship between these two variables and did it by looking at a graphical model or a graph. We can use this, possibly most importantly, we can use graphical models to develop our mathematical models or equations. And I'm betting you've even done that before. The way that we would do it is, this won't be a straight line, but I'll do my best. I could draw a line of best fit through here. And if I really wanted to, that line of best fit is going to have the equation y equals mx plus b, right? Right. Sorry, that's a b, right? You've learned that. That's the equation for a line. Well, this is an equation, and that equation describes this relationship. So I have just gotten a mathematical model / equation from a graphical model. And from there I can use predictions. So I want to talk about briefly some of the most common ones we'll see in here. The most common relationship we'll probably see all the time, all year, is our linear relationship. So in linear relationships, as independent variable increases, so does the dependent variable. So as in this case, as time increases, so does speed. And because this is a relationship that I can draw a straight line through, or with the trend line, I'm going to get a slope, right? This line is going to have some slope. It's the y equals mx plus b. And so it is, that slope is this, is m. And so really, in a perfect world like this one, b is 0. The y-intercept is 0. So really, what equation describes this? Y equals mx. If b is 0. So in this case, I can substitute it in for variables. What is the y variable? Well, it's speed. What is the x variable? Well, it's time. And so whatever this constant is, it is the number that if I take it and multiply it by time, I would get to learn something about my y variable. So again, linear relationships are really nice because they allow us to, just using the slope, understand the relationship between the y and the x variable. And there's a little more to it, but we'll practice that together in class. Another type that we are going to encounter are parabolic relationships. So as the independent variable increases, so does the dependent variable, but this occurs at a changing rate. So sometimes I think if I just showed you this before, you'd say, oh, it's growing exponentially. And that's true, right? Like if I included the other half of this, it would make a parabola that you've seen in math class. But if we just look at one side, looks like it's growing exponentially. And so to describe that relationship, we would use an exponent, whether it be 2 or 3 or 5 or whatever we determine it to be, to describe this. So in this case, an object's position, m, is equal to time, but it's not a straight line, so I can't just put slope in there. It's time squared. Again, there's more to this, and we'll get to it. I just wanted you to, at this point, recognize the shape. So in this case, if you see it exponentially, you could call it exponential, but it's really a better way to describe it is parabolic. And then the last one we're going to look at are inverse relationships. So in inverse relationships, we have as independent variable increases, the dependent variable decreases. And this occurs at a constant rate. I know that doesn't necessarily look like it, but it is. And again, this is something that we will encounter more of as the year goes on, but we would need to use, since this is an inverse relationship, as volume increases, pressure goes down, right? That's what our graph is showing. And the way that we get that mathematically is we use the inverse relationship. So instead of P being equal to V, P is equal to the inverse of V. The inverse of V is 1 over V. And that rate is constant. So again, we'll encounter that later on when we're actually doing some physics, and we'll talk about it later on. I just wanted you to see the relationship. This is an inverse relationship. Okay, I just want to show you how to analyze a graphical model. So assuming you do some lab and we'd collect a bunch of data. So the first step is to create a scatter plot. If you don't know how to do that in Sheets or Pivot, then go back. There's supplemental questions and text about this, and a video even that I created on how to put data into Sheets and do all this. So you might need to go back there. I'm assuming that at this point you have some skill, proficiency in creating a scatter plot, not a line graph, but a scatter plot. If not, jump back. But once you have your scatter plot, so it's going to look like a bunch of points in there, you would then add a line of best fit. Again, I show you that in the tutorial. So here's my line of best fit, and then assuming that line is a good fit of the data. If it's not, we'll talk about what happens if it's not. I would get an equation. So here I've plugged in some numbers. I would get the equation for this line. The computer will tell me that, and it'll give it to me in the equation y equals mx plus b. So when I do that, the equation that this gives me is, and I guess I forgot to put it on the screen, but the computer spits out at me, it says y equals 0.30 x plus 3.2. So that's the equation that the computer gave me. But this doesn't tell me anything, it's just numbers and symbols. So I need to actually interpret this. And so if we look at this, we know some things from math class that we learned in math class. I know the slope of this is 0.30. But 0.30 what? Well, slope is rise over run, right? Change in y over change in x. So really what this is telling me is this is 0.30. So another way to write this would be 0.30. And what is the unit? These aren't just numbers anymore, these are units. Y has a unit. So 0.30 centimeters over, well, what's x? X is 1 for every 1x. And then again, it's got a unit. X has a unit, it's grams. So my slope is 0.3 centimeters over 1 gram. So we're giving some meaning to this. And my y-intercept is 3.2. So now I can substitute these in with units. I can get rid of y. I don't want to call it y. Y isn't just a y anymore. It's an actual thing, and neither is x. It's mass. So I can write a mathematical model from this. Stretch of a spring, so how much a string stretches in centimeters, is equal to 0.3 centimeters for every gram. So for every gram of mass I add, it stretches 0.3 more centimeters plus 3.2 centimeters. Okay, so let's talk a little bit about what that actually means. So interpreting these, here's my equation again. String stretch is equal to 0.30 centimeters per grams times the mass plus 3.2. So we know slope is change in y over change in x. We talked about that. A good way to think about this when you're describing slope, because it's something you're going to have to do, is being able to say for every one x unit, or the dependent variable, the y changes, the y variable, the independent variable, changes by some number. So in this one, since my number was 0.30 centimeters per gram, I would say for every 1 gram of mass added, the spring stretches 3.3 centimeters more. And so now I'm just not saying what is the slope. Oh, 0.3, what does that mean? I don't know. I'm telling you what it means. 0.3 means for every mass of a gram I add, it stretches further. Y-intercept tells me something too. In this case, it's 3.2. So what does that tell me? Well, the y-intercept is the x or the y value when x is 0. So when x is 0, that means there is 0 grams of mass on there. So what exactly does that mean? Well, so that means that before any mass is added, so when mass is 0, the string already has a stretch of 3.2 centimeters. So if I'm thinking of this setup, and I've got this spring hanging from something, that means that even with no mass on it, it already is stretched 3.2 centimeters. And that's going to matter to me when I'm doing math and physics and measurements. All right, so hopefully that helped not only give you an idea of how to create graphs and interpret them, but also why we use graphical and mathematical models. As always, if you have any